Welcome back to this series on analyzing systems of gears. In the last video, we developed the rolling contact equation for a pair of gears rolling externally. And if you haven't got a chance to watch that, I recommend that you go back and watch that video because we're going to pick up where we left off in that video to analyze a gear system with compound gears. But before we start with equations, we're going to define a new way of depicting gears and how they mesh with each other in gear systems. So imagine that we have a cross section like this, and so from our last example we had gear X and gear Y. That would look like this right here. This would be gear X and this would be gear Y. This horizontal line represents the axis of gear X and this horizontal line represents the axis of gear Y. These horizontal lines basically just represent the circumference of the pitch circle of the gear, like that right there. And this is where the two gears X and Y mesh together. The reason it's beneficial to depict the gears like this is because in large gear systems it can become difficult to see which gears are in mesh and which ones are actually sitting on a different plane. So for example, I might have a gear behind Y like this, but it still spins on the same axle. Now let's look at a compound gear. I'll call this gear 1 and this gear 2. These two gears are physically joined together, so they act as one gear with two radii. And it's going to be beneficial in the rolling contact equations to also treat them as a single gear with two radii. So we would call this gear 1, 2. Let's see what the depiction of the cross section of gear 1, 2 looks like. So this would be gear 1, this would be gear 2, and the axis is right here. Now I'll start hiding some of this and go ahead and put up an example. Here's the example. Before we get into analyzing the gear system, I want to go over some of the nomenclature in this depiction. The yellow lines with hash marks represent the ground. This axis here is connected directly to its gear and spins with it, so we call it a spindle. It's supported on both sides by the ground, which would be a bearing or a bushing of some sort. Now let's look at the other two gears. This gear has a stationary axis as indicated by the yellow hash marks, which indicate the ground. Same with this gear, which is a compound gear. When we have an axis that is stationary with the gears spinning on it, we call it an axle. So we have spindles and axles. Let's just put that up here. This is the convention that we're going to use for all the examples going forward. Now let's hide this and let's get started with our analysis. And the first thing that we want to do is we want to go through and label all of the elements of our gear system. So we'll start with the ground and we will call that 1. And then we'll move on to the first gear and we'll call that element 2. And then the second gear we will call 3, 4, and 5. Now, as you may recall, we said 3 and 4 are connected together, so we're actually going to analyze that as a single gear, and we're going to call that gear 3, 4. For this problem, we want to find the gear ratio. So like last time, we're going to use the rolling contact equations for external gears to do that. But that time we had only a single pair of gears. Now we have 3 gears, with one of them being a compound gear. The first thing we want to do is identify how many rolling contact equations we're going to have. So what we want to do is look and see where are our rolling contacts. Well, gear 2 rolls on gear 3 and gear 4 rolls on gear 5. So there's 2 rolling contacts, so we're going to have 2 rolling contact equations. The next thing we want to do is identify the arms of the rolling contact. So remember, that's the vector extending from the center of one gear to the center of the other gear. And in this case, gear 2 just rolls on the ground, as well as gear 3 rolls on the ground. So in this case, the arm is just the ground. And in fact, it's the same with gear 4 and gear 5. If we extend a vector down from the center of 4 down to the center of 5, we'll see that gear 4 rolls on the ground and gear 5 rolls on the ground. So this arm is also just the ground, which is really pretty common. It's not until you start looking at planetary gearboxes or differentials so that you start getting some moving arms. Now let's write out the relationship for each pair of rolling gears, which will define the rolling contact equations. So for the first pair, gear 2 rolls externally on gear 3, 4, which remember we said gear 3 and gear 4 act as a single gear because they're physically connected together. So it acts as a single gear that we call 3, 4 with two different radii. So 2 rolls externally on 3, 4 with respect to the arm 1, which is just the ground. So that's the first one. And the second one is gear 3, 4 rolls externally on 5, also with respect to arm 1, which is the ground. Now let's express these mathematically. We'll start with equation 1. Gear 2 has a radius ρ2, and we multiply that times the change in the angle of gear 2 with respect to the arm 1, which is the ground. And that's equal to, whenever we see an external rolling contact, we know that we need this negative. So negative ρ3, because we're looking at gear 3, 4, and we said that gear 3, 4 is a single gear with two radii. And in this case, where it meshes with gear 2, it has a radius of ρ3. So we're going to multiply that times the change in the angle of 3, 4 with respect to the arm 1, which is the ground. And in equation 2, gear 3, 4 has a radius of ρ4 where it meshes with 5. So we multiply that times the change in the angle of gear 3, 4 with respect to arm 1, which is the ground. And that's equal to a negative, because it rolls externally with 5, ρ5, the radius of 5, times the change in the angle of gear 5 with respect to the arm 1, which is the ground. Now I'm going to make some room on the board and put equation 1 back up here. And now let's expand this equation. So we have ρ2 times the change in the angle of gear 2 relative to the change in the angle of arm 1, which is delta theta 2 minus delta theta 1, is equal to minus ρ3, again the change in the angle of gear 3, 4 minus the change in the angle of arm 1. Since arm 1 is the ground, there is no change, so this is 0 and this is 0. So the equation becomes ρ2 times delta theta 2 is just the angle of theta 2 minus the initial angle of theta 2, so theta 2i, which is equal to minus ρ3 times the angle of 3, 4 minus the initial angle of 3, 4i. Right now this equation is in terms of the angular positions of gears 2 and 3, 4. What we're interested in is the relationship between the speed of gear 2 and the speed of gear 3, 4. So right now we're going to differentiate the equation with respect to time, so it'll be in terms of angular speed. Differentiating gives us ρ2 times the derivative of theta 2 with respect to time is the speed omega 2, and theta 2i is a constant, so that would be 0, which is equal to minus ρ3 times the derivative of theta 3, 4 is the angular speed omega 3, 4 minus theta 3, 4i is also a constant, so that would be 0. Simplifying this a little bit gives ρ2 times omega 2 is equal to minus ρ3 times omega 3, 4. Let's make a little bit of space and put equation 2 back up. Equation 2 was ρ4 times delta theta 3, 4 relative to 1 is equal to minus ρ5 times delta theta 5 relative to 1. Since we've already gone through the exercise of expanding equation 1, I'm just going to go ahead and differentiate this equation with respect to time, and you can see how fast this actually goes. So we have rho 4, the derivative of delta theta 3, 4 with respect to 1. 1 is the ground, it doesn't move, so it's just going to be omega 3, 4 is equal to minus rho 5 times the derivative of theta 5 is just going to be omega 5. Now let's solve for omega 3, 4, which is equal to minus rho 5 over rho 4 times omega 5. And we can substitute omega 3, 4 in equation 2 into equation 1, and we get rho 2 times omega 2 is equal to minus rho 3 times a minus rho 5 over rho 4 times omega 5. And then if we solve for omega 2, we get omega 2 is equal to, the minuses cancel, and we have rho 3 times rho 5 over rho 2 times rho 4 times omega 5. If gear 2 is our input and gear 5 is our output, then by definition of the gear ratio, we would say that R is equal to omega in over omega out, which is equal to omega 2 over omega 5, which is rho 3 times rho 5 over rho 2 times rho 4. And if we want, we can express it in terms of the gear teeth instead of the radius, which should just be N3 times N5 over N2 times N4. That's the gear ratio. One thing to notice is that it's positive, so that means the input gear and output gear are spinning the same direction. So you can see how we could add more pairs of gears, and we're just going to get more rolling contact equations, which would just require a few more substitutions to relate the input speed to the output speed to solve the gear ratio, but it really doesn't make it any more difficult. Be sure to check out the next video. We're going to look at idler gears, how they affect the gear ratio, and why you might use them. If you like this video, please give it a thumbs up, subscribe if you want more, leave your questions and comments down below, and thanks for watching.